Hello. In this video, I'll explain the partial pivoting technique used with Gauss elimination method when some elements in a system of linear equations have special values. In any given linear system, zero elements may be located anywhere in the matrix of coefficients or the vector of the constant terms. If the zero elements are above the main diagonal of the coefficients matrix, they do not affect the calculations at all for two reasons. First, they don't take place in the elimination factors or multipliers. Second, if they are not in the fixed row, they can be changed to non-zero values due to the subtractions of rows during the elimination process. A zero element below the main diagonal can lead to division by zero if it is located in a column to be eliminated. For example, the zero in the first column in this matrix will be in the factor that will be multiplied in the whole row. As explained in the last video, this problem can be avoided very easily just by skipping the elimination process for that row, since it already has a zero in the required position. Meanwhile, the zero in the last row could be replaced by a new non-zero value at the first elimination. The most critical location of zeros is the main diagonal because these elements are included in the elimination factors of each row. The solution to this problem is to interchange the rows by using the partial pivoting technique. Zero elements in the B vector do not affect the calculations, but depending on the given system, they affect the solution. For example, if all elements in the B vector are equal to 0, all values of x will be 0. The pivot or the pivot element is the first non-zero element in the fixed row. It is used to calculate the factors to be multiplied in all elements of the rows below the fixed or the pivot row. As you see here, in the original system, the element A00 is the pivot. After the first elimination, the element A11 will become the pivot, and so on. The idea of the partial pivoting is very easy. Just interchange the whole pivot row with another row below it to place a non-zero value in the pivot position. Of course, the corresponding constant terms elements in the B vector should be interchanged too. Otherwise, the solution will be wrong. It is called partial because the interchanges are applied to the rows only, while the columns are not changed. We need to apply the elimination of a three-equation system. The pivot element A00 is equal to 0 here. So the first step of the solution will be to interchange the rows 0 and 1. So in this way, the pivot element A00 will get a non-zero value. Remember that one of the properties in the linear systems is that interchanging complete rows in the A matrix and the B vector do not change the final solution of the system. After replacement, the zero element is now in the pivot column of row 1. So we skip the elimination process to that row. By eliminating the last row, we get zeros for all elements under the main diagonal, as we see here. Now let's see the algorithm of the partial pivoting technique. So the partial pivoting should be applied at the beginning of each elimination. So it will be inside the K loop, which goes through the fixed rows in order to perform elimination in the Gauss elimination method. The partial pivoting starts by checking the absolute value of the pivot element AKK. If it is equal or approaches 0, then we start a loop, which we call it I loop, which goes from the next row to the end of the rows in the system. So if any element below the pivot 1 is larger in absolute value than the current pivot element, which is supposedly equal or approaches 0, then we start the interchanging of rows in the system. So we begin by interchanging the two rows AI and AK. This sign, which is the colon here, refers to all columns or to all elements in that row. So we will replace, or we will interchange the both rows completely. Then we interchange the corresponding B vector elements. At the end, we should break the I loop. That means we return to the K loop and continue the elimination. Now, let's see an example in order to see how to code this algorithm in Python. In this example, this system contains two 0 elements in the first column. So it should be modified by using partial pivoting before the elimination. Now, we start coding of this tutorial from the Gauss elimination script we developed in the last video. As you see here, we started with the definition of A and B arrays of the given example. Now, before starting the modification of the code, let's run the current code of Gauss elimination without adding the partial pivoting and see the result. So as you see here, there's an error which has resulted during the back substitution stage because we need to divide by A's, and because of they are multiplied by zeros, so such an error is expected. And the solution, all elements are not numbers because of division of 0 by 0 in the running time. Now, let's start the modification by defining the lines or the algorithm in Python code. So we start just after the line of definition of starting loop, K loop, as we mentioned in the algorithm, and we check the absolute value of AKK. Now, for absolute value, we can use a NumPy function called FABS, which checks the absolute values of float numbers. But before that, we should include or import this function from NumPy in order to be defined during the coding. Now, as you see here, we can write this statement and it's correct, but it has a problem. It does not include the very, very small numbers which approach to 0. So this statement checks the zeros only. But imagine if there's a number which is like 1 multiplied to the 10 to the power minus 12 or 15, which practically 0, but in computer language it's not 0, it's a very small number. So the more flexible way is to say if the absolute value of AKK is less than, and we assume our smallest value, let's say for example E minus 12. This depends on your problem and how much the small value is considered 0. Now we can go to start our for loop. Now we can interchange or swap the lines or the rows in this way. So actually in this way we are telling the interpreter to switch or to interchange the I and k. So the indexes will be replaced in a manner that makes the rows interchange in the A matrix. The same thing can be done with the B. Now, finally, we write the break statement in order to return to the K loop to continue the elimination. Now, this is the application of the algorithm. Let's check by running the code. So as you see here, we obtained this solution and there's no any errors in this run. But we need to be sure that this solution is correct. So let's do something. Let's compare this solution by the solution we can get by the NumPy solver. So we include the linear algebra module of NumPy, and before making any changes in the system, because during the elimination we will change, create some changes in the system, which all elements under the main diagonal will be zeros and so on. So here we need to check the solution before making any changes on the A matrix and B vector. So we say print of NumPy, and we say print linout.solve. So this is linear algebra solver of the A and B. So this is the syntax used in order to show the solution. Now let's run the code again. So as you see at the top, we have the solution of NumPy, and when you compare it with the solution of our code at the bottom, so they are totally identical. If you like this tutorial, please hit the like button and don't forget to subscribe and turn on the bell to be notified for the coming videos. Thank you.